Welcome to week 8 of our NPTEL course on muffler acoustics. So, since the last week we have basically moved more towards the business end of the things, really stepping into analysis of commercially used mufflers, which are perforated mufflers. So, after developing some of the background, some of although very briefly, the background required for dealing with such stuff where mean flow is present, like aeroacoustic state variables and introduction to perforated elements. What we will do in this week's lecture, a majority of the part of the lecture will be a detailed analysis of CTRs, concentric tube resonators, which is either fully perforated, that is basically it is a counterpart of a simple expansion chamber, concentric simple expansion chamber, and otherwise it can have only a partially perforated airway or a central duct through which air passes, and it is only partially perforated from either sides. So, this serves to develop some sort of a quarter wave resonators or neck extensions at the inlet as well as at the outlet. Okay. So, the purpose of such a thing is basically so that the resonators that are formed at the inlet and outlet, at the resonance frequencies of such quarter wave resonators, the attenuation produced is maximum, and that would completely annihilate or completely overcome the troughs that would form if such extensions were not there. It is exactly the same as extend inlet and outlet thing, where the peak due to the quarter wave resonator at the inlet is able to nullify or cancel the trough that would occur at the first resonance, whereas the peak at the due to the second or the quarter wave resonator at the outlet, it is able to nullify the second resonance and so on. So, we pretty much apply the same technique, but again, like I have been mentioning time and again, it is basically the perforates that are very crucial and they help in guiding the flow, and we need to develop, they act like a bridge really. So, although extend inlet and outlet have been studied a lot, relatively lesser focus is there on CTRs with neck extensions. So, in this lecture we will go through a detailed development of the transfer matrices for such a thing, incorporating the effects of mean flow, and you probably go to MATLAB to help us with some of the parametric studies where mean flow is involved, and we can also possibly take into account the effect of end corrections, at least for a stationary media. Okay. In the last class, I guess let me go to the last slide. So, we stopped somewhere here. Okay, B inverse, B will be when Mach number is 0, that is basically this case, Mach number when it is 0, it will not be an identity matrix because of the particular arrangement of the state variables, that is alright. But in any case, even when m naught is 0, this is not inverse, it will be 1. So, there is no problem in that. When it will be not 1, then we have to invert this matrix. So, for argument's sake, let us call this B inverse A, let us call this B inverse A as C matrix, okay, which is in this case a 4 cross 4 matrix. All right, this is what we get. We get this part. So, the question now arises, how do we solve it? So, typically what is known as a generalized decoupling method and other things in the literature is basically the same thing can be solved in using just one line command in MATLAB using a exponential function, matrix exponential function. So, basically let me do some simple linear algebra things. So, e to the power we already know the function, isn't it, 1 plus x exponential function x square by 2 factorial x cube by 3 factorial and so on. So, if a matrix is now raised to the power e to the power a can be some matrix. For argument's sake we will keep this as C matrix. Okay. So, this is given by defined as C matrix plus C square 2 factorial C cube 3 factorial, it is defined like that. And how do we compute that? That is a separate matter. You need to find out the eigenvalues and eigenvalues matrix when it is written side by side, inverse of that into the is basically part of the linear algebra. So, I will not go into the fact that how this guy is computed. It is defined like that, or it is defined like that, but in MATLAB what you just need to do is that type exp_m and give C. So, it will basically shoot out you some matrix D is equal to exp_m_c. So, it will compute this using some algorithm that is there in it. Why is this useful to us? Now, because let me take a small digression here. Let us say we have a simple first order ODE, so what is the solution of this? Okay, y is equal to alpha e to the power ax, a is known, alpha is the constant which needs to be determined from the one boundary condition, because if you put this thing, LHS and right hand side will be the same, where alpha is the arbitrary constant. Now, similarly, if we were to propose a solution of the form of this equation, x vector is nothing but your say e to the power C matrix times z. Remember, we need to integrate with respect to z. So, here we have this, and the constant, let me call that constant some number, let us say q. Okay. Q is basically a vector of unknown constants, that is basically q1, q2, q3 and q4. Okay. So, this is the solution. Why is this a solution? Because it is easy to see that, I mean, if we were to substitute this solution into this one, LHS and RHS would be the same. You will eventually get back C matrix times this thing, because suppose if we differentiate, we expand this guy using this formulae and differentiate with respect to z. So, we get I plus C z, Cz square, z square and so on. So, if we differentiate, this term will be 0, and what will we get is basically C plus your C square, but here will be the denominator will be only 1 factorial C cube, and here we will have 2 factorial and so on. So, and eventually we can just take C common and realize, and this will be z here, and realize that z square, I am sorry for that, that we are eventually left with this thing C square by z square by 2 factorial and so on. So, let me move to the other page. So, we will be getting C e to the power C z again, and there is a constant like I said q here. So, if we differentiate this, so this is nothing but this underlined terms only from here to here, this is nothing but C matrix times x, because that is what we proposed, is not it. So, this is x. So, basically if we differentiate this guy with respect to z, we will get back this solution, and this happens to be this particular guy, this happens to be our RHS. So, in short, what I am trying to say is that this solution, this particular form of the solution always satisfies our differential equation, ODE, a set of linear first order differential equations. So, if we do the matrix exponential, we will get this, and in MATLAB, like I said, all we need to do is like it will pop out some matrix D is equal to exponential exp_m, not exp, just exp_m_c. So, you can have fun with this thing, and q is a constant which needs to be determined. So, let us say we have this solution. So, we will move on from here. Now, our job now is to determine. So, let us go back, let me draw it again for you anyways. So, this is our perforated bridge section, is not it, and we have the duct 1 here and 2 here, annular part. Let us say we are fixing a coordinate system z is equal to here at this point and z is equal to L. Okay. So, now what do? We are fixing a coordinate system at these points mentioned here, at point A and B, z is equal to 0 and z is equal to L. Our first job now is to determine the constant q in terms of the state variable at, we will call simply this as x0 and xL. Okay. So, we know the solution in the form this thing. So, x is equal to e to the power c at z is equal to 0. This is just 0, which is your identity matrix. So, I will simply write this as identity matrix times the vector q at 0. Okay. So, this becomes at z is equal to 0 simply the vector q. Okay. So, now vector x at any point is your e to the power c z into x 0, is not it? Now, we want to relate things at z is equal to L. So, what we need to do is that at z is equal to L, this becomes e to the power c is L. We will simply multiply the matrix C, each and every element of the matrix C with L, and multiplied here is your vector here. All right. So, eventually what do we get? So, if you recall, transfer matrix representation obviously relates things at the upstream with those at the downstream. So, we need to invert it. So, at x is equal to 0, we relate things with those at z is equal to L. So, what happens is that e to the power c L inverse of this matrix at x is equal to L. Okay. So, we will sort of get this. So, this can obviously be written as e to the power minus, or we will just, it's a matrix. So, we will take this inside, this guy inside, and okay. So, we do get that, all right. So, we get this representation. Okay. This becomes very simple now. Just in MATLAB, you would just probably do exp m, and we will just say minus c L. So, we can just multiply the number L, length L, or the perforated section to each and every element of the C matrix, that is basically B inverse A, and put a minus sign and just give this command. So, this whatever this guy is, whatever this thing, we can, for just for our convention, we can, just for our simplicity, what we can do is that we can say this is your, let us say, your T matrix, okay, and here T is 4 cross 4, and your x L is 4 cross x 0 or x L is 4 cross 1. Okay. Let us expand this out, and let us do this. Here tilde 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 So, this is an expanded out form of this guy, and here we will have, this is at z is equal to 0, and O naught C naught U tilde at z is equal to L. Okay. So, this is your fully expanded out form. Okay. So, for simplicity, let me put this dotted lines. Okay. Now, where do we go from here? So, what needs to be done at this stage? So, we have got a solution at least symbolically. We would need to use computer algebra, otherwise hand calculations even for a simple 2 duct interacting system can get very messy. So, often you have multiple interacting ducts. In principle, it's possible to get things like this kind of a thing. You have multiple perforated ducts, something like this, and you have like this, and then you finally have this kind of thing. It forms basically your multiple extensions. So, multiple neck extensions are there. In principle, you can have any. So, you can have systems like this, and the flow comes in from here, and let me just sort of complete this figure, and similar thing would sort of exist here. We have this kind of a thing. Okay. So, you can have multiple such things. Imagine if you were to do all this by hand calculations, all right. Things would become just impossible, solving like this is like 1, 2, 3, 4. So, each duct has 2 variables. So, something like 8, 4 into 2, that is 8 cross 8 matrix. So, it becomes almost impossible to deal with such a coupled 8 cross 8 system, or the 8th order differential equation if you were to combine all of the variables into one. So, it becomes quite messy, and then that is the reason that it is best to work. I would prefer working in terms of a set of coupled linear ODEs and keep it first order. So, MATLAB or any other algorithm would do it pretty efficiently for you. Even if you do not rely on this thing, you can always write algorithms to find out matrix exponential. So, the idea is definitely to use some computational algorithm rather than seeking analytical solutions, because perforated ducts really requires that, especially when you have mean flow. So, I will keep this figure just like that and sort of move on. So, I would like to remind ourselves back that this is the system that we originally intended to study. We intended to study this. Okay, we intended to study this. All right. So, how do we go about this? Now, we have got this system and we would like to impose the boundary conditions. Now is the time to do that. Now, clearly, as you can see from the figure, that this is a partially perforated section. So, at z is equal to 0, at z is equal to L, we have this. So, what about the annular cavities 1 and 2? Let me 1 and 2 is the use for this duct. So, let me use some other term. We will call it A and B. Okay. So, if for the portion A, that is the cavity formed here at the extension at the inlet, if the length L A and L B are 0, then it obviously reduces the case to the case of a fully perforated expansion chamber, fully perforated concentric tube expansion chamber, something like this. It is fully thing. So, let me just draw this thing again for you guys. So, it is something like this. Apologies for the color. We have holes everywhere, perforates right from the beginning all the way until the end. So, things would become sort of fairly simple. Let me derive this sort of a thing for you guys, and then we will perhaps do some get back to this equation again and involve then neck extensions. Okay. So, we will do that. So, what happens here really? So, U2 is the stuff where we need to apply the boundary conditions. Remember, this is the duct. So, really what we have is that U2 is equal to 0 at z is equal to 0 and z is equal to L, because your this thing is kind of squeezing, or basically you have kind of extended the duct perforated section throughout the chamber. So, your z is equal to 0 starts from one of the faces and z is equal to L is at the other end face. All right. So, you have this sort of a thing. What it means for the transfer matrix that we have derived here, let me use the red color. So, U2 at z is equal to L is 0, as we have just noted here, this is the condition. Okay. So, what it would mean is that we do not have to deal, this is multiplied by this with this with this, but then this guy is 0. So, we can get rid of this particular column, okay, because we do not have to deal with this. Similarly, u2 is also 0 at z is equal to 0. So, what it would mean is that this into this plus this into this plus this into this is 0, but we would like to sort of relate these two guys with these two guys. So, although we have eliminated u2, but we still have T13 multiplied with P2 and T23 multiplied with P2 also, and we have one more relation, P2 is related, P2 at z is equal to 0 is related to the other variables in the downstream using the third this thing. But in the process we also found out another relations, T41 multiplied by P1, T42 multiplied by this rho naught C naught U1 tilde, T43 multiplied by P2, linear combination of this is equal to 0. From that we can get some equations for P2, I mean express P2 in terms of these two quantities, and then basically put that P2 in the first two equations and simplify things. Let us sort of get started with it, that we will put T41 P1 tilde plus T42 rho naught C naught U1 tilde plus T43 P 2 tilde is equal to 0. Okay. So, what this would mean is that P2 tilde is your nothing but T41 P1 tilde plus T42 rho naught C naught U1 tilde. This is of course at z is equal to L, all of them. So, this happens and T43. Okay. So, this is there, and so we get this guy, and this is like I said at z is equal to L. Okay. So, now we will keep this equation, let us call this equation 1, we will keep this equation 1 aside, and in the other chunk of equations, now we need to focus really on this guy, this entire thing is multiplied by this thing. So, basically P2 will come in here. So, let us do the maths. Let me go to another slide. So, where I put P1 tilde and rho naught C naught U1 tilde as something like this. It is going to be a bit messy. So, I am kind of forewarning you about the things. So, be a bit patient with the simplifications. What I would strongly recommend to all of the students here in the class, especially the ones who are certain to take up the final exam and are doing assignments, is that please work out the algebra on a piece of paper, and using the longhand approach, that is very important. Otherwise, you will probably never be able to understand or appreciate things, otherwise it is just like this. So, this is z is equal to L, and of course, I am sorry, there is a mistake. So, I should have written this the last. So, this is P2, my mistake, sorry. So, z is equal to L. Okay. So, this is 2 cross 3 and this is 3 cross 1. So, you get 2 cross 1. Now, using equation 1, we need to eliminate P2. This is of course at z is equal to L. Okay. So, P2 thing will be put in here. So, let us sort of do that. It is going to take the entire thing. So, I am not going to bother writing with this T11, T12 and T13, T21, T22, T23, and what we will get P1 and rho naught C naught U1, and now it is the time to substitute all these things in here. So, what we will do is that the first term here would be minus T41 by T43. So, minus T41 by T43, and into P1, isn't it? P1. So, I am not writing at z is equal to L, it is sort of very well understood. So, minus T42 by T43 at T4 this thing, and so we get this thing. So, what this thing is there. Now, we have really this equation. Okay. So, now we need to do term by term multiplication of each of the parts and rearrange the things. So, what I am going to do is that I am just going to go like this and start to multiply T11 times P1 tilde, T12 times rho naught C naught U1 tilde, and now multiply this chunk with the entire thing. So, this is going to be the part that requires a little bit of patience and a lot of concentration. So, my request again is that please do these derivations for yourself on a piece of paper, maintain a separate notebook, those who are at least taking exams and are serious about this one. So, T42, T43, rho naught C naught U1 tilde. Okay. So, let us first simplify this particular first row. So, this would, or rather let me just sort of write down the second row itself, and it's then we will simplify all of that together. So, T22 rho naught C naught U1 tilde. So, again you will get 2, 2, 3 P1 tilde and minus T23, T42, T43 rho naught C naught U1 tilde. Okay. Now, we can comfortably combine these guys into the following. So, we get T11 minus T13 T41 T43 times P1 tilde plus T12 minus T13 T42 T43 rho naught C1 U1 tilde. Okay. So, this is the first equation. The other one is T21 minus T23 T41 T43 P1 tilde plus T22 T23 T42 T43 rho naught C naught U1 tilde. So, this is your second row. So, now I guess we are in a position to relate things at the upstream of a CTR with those at the downstream. So, okay. So, we get this okay, and here of course we get P1 at z is equal to L. Okay. This is how it looks like. Now, the big transfer matrix is finally reduced to a 2 cross 2 matrix, where we have related things what goes on at this point to this point, where your z is really stretched, z becomes here at 0 and z is equal to L here. So, it is a fully perforated pipe, and we have related things just here to that somewhere here, z is equal to 1 to z is equal to L. And so, this is how it looks like, in terms of flow. Well, flow is there implicitly because if you recall, we are calling this entire guy V inverse A as C and e to the power C Z, that is your T matrix, and so all these manipulations will eventually lead you to this form. So, now since mean flow is there, and as we can see your diameter of the inlet and outlet is also the same. So, the transmission loss expression would really basically sort of result back to the one that is used for classical state variables, because you remember you have a term like 1 plus m I and 1 1 plus O, I and O means inlet and outlet, or maybe the other way around. The main thing is that these things will cancel out because they are the same. So, eventually in terms of the final matrix, you can call this matrix as T1 matrix. So, you can call this entire thing as T1. So, T1 matrix which relates things here. So, the transmission loss will be completely decided by this particular matrix, and you can use the expression for the classical state variables as well in this case. So, we have analyzed at least symbolically a fully perforated concentric tube resonator. What we now have to do is basically the way we will go about doing the derivations from now is that we will sort of get the things for the extensions, when you have extensions at the inlet and outlet. So, there what are the boundary conditions and how do we go about that? Okay. So, let me sort of do the derivation again for you, but with sort of different boundary conditions. So, it is going to be much more tedious than this case, because now you have your other impedance expressions in terms of cot or tan and all that sort of a thing. We will probably put that later, but the funda is the same, the main idea fundamentals are the same. So, let us do that. So, what we are going to do now is analyze, basically figure out the transfer matrix for a concentric tube resonator, but with extensions at the inlet and outlet. So, we probably we are looking for a solution of this sort, but only thing is that now we have our neck extensions also there. So, let me draw a rather clean image of this, and somewhere like in here. Something like this. Okay. So, the flow goes something like this and leaves here. Okay. So, what we want is the stuff between, this is z is equal to 0, z is equal to L. Like I said, this part is A, B. So, it is quite clear now that this is duct 1, duct 2, all right, and this can be circular or elliptical in shape, whatever it is. There are a couple of things that sort of needs to be clarified right at the outset, is that looking into the cavity, velocity direction is taken or positive along this direction, that is along the direction that I am pointing somewhere here. So, looking into the cavity like this is basically what you will do is put the impedance P 2 tilde at 0 and rho naught C naught U 2 at 0, but here you will have a minus sign because it is looking into the cavity. So, this is equal to your minus j rho naught C naught. Note that it is not y naught, because we are kind of changing the acoustic velocity variable. It is not a mass velocity any longer, it is a non-dimension, or a velocity variable has the same dimension as pressure. So, it is cot k naught L A. So, this length is L A. Okay. So, this length is L A and L B. So, we have this sort of a thing, and P 2 by rho naught C naught, this is L is equal to minus j times rho naught C naught cot k naught L b, where L b is the length like I mentioned. So, this of course, we are looking into the cavity like this, all right. So, with this boundary condition, now here we do not have u 2 and u 2 at 0 equal to 0, neither we have u 2 at z is equal to L 0, although I must mention here that these plates, these end plates, they are rigid. So, that much we know of. What does this mean? That is why we have this cot k naught expression. But now using, let us say, the boundary condition 1 and 2, we would like to eliminate some variables, that is your P 2 and rho naught C naught u 2 at z is equal to 0 and z is equal to L. We would want to eliminate that, and let us see how we sort of go about our business. So, well, we have this. So, well, in terms of P 2 at z is equal to 0, we have this thing. So, what we really can do is that divide P 2 at z is equal to 0 by this thing. So, we have your divide this by minus j rho naught C naught cot k naught L a, I guess, but you also have a minus sign sitting in here. So, this would be plus, all right, and this entire thing can be written something like this. Note that the transfer matrix parameters themselves would not really change, it is just that the boundary conditions are different. So, eventually the final matrix T 1 matrix, that will change. So, we have this. P 1 and rho naught C naught u 1 P 2. Now, again here we need to do the same trick, rho naught C naught u 2 goes on the numerator and this guy comes down. So, this would be P 2 by rho naught C naught cot k naught L b, and here will be minus. So, we have this sort of a thing. So, what we can possibly do is that you have a minus sitting in here. Okay. So, if we take the minus here and minus here, 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 then we can possibly get rid of the terms in here, isn't it? So, this is cot k naught L b. Sorry for my handwriting, but that's what it is. So, we've done well so far. Now, what we really need to do is, as usual, we need to relate this two guys with these two guys, and in the process eliminate P 2 somewhere here. Anyways, we have reduced now the things to only 3 variables. So, we need to wisely use the equation. So, as usual, we start from the this row. So, this one into this into this, T 1 3 into P 2 and T 1 T minus 1 4 into again. So, P 2 can be taken common in this set of equations and also on this one, and then we have sort of another relation you can choose whatever we want in terms of we have actually variables here. So, we have two more equations. Let's sort of cleverly do it. It's going to be a little bit involved algebra. So, please bear with me in the derivation. So, P1 tilde and rho naught C naught U1 at z is equal to 0. So, I am just writing 0 here with the understanding that this is at z is equal to 0. T11 into P1 and T12, and now what we have to do is T13 into P2 and minus T14 into P2 rho naught C naught cot K naught this thing. So, we can now really combine these two things. So, T13 and minus T14 rho naught C naught minus T14 into P2. So, P2 is common, rho naught C naught and cot becomes tan, okay. Cot K naught L B, okay, and this guy becomes at z is equal to L, all right. So, and here it is the same old business, and here also divide by rho naught C naught. What we will sort of get is P2 is common. So, cot goes in the numerator, cot goes in the numerator. So, here we will have tan, but I guess I am probably making a small mistake. I realize now, sorry, it's a small mistake. So, here I think I kind of did something very elementary mistake. So, this cannot be this thing. So, here we have this, and similarly we have P2. My sincere apologies for the small error, but we will sort it out now in this equation. So, basically what happens is rho naught C naught still we would want rho naught C naught. So, basically we have minus minus plus. So, the only thing is that this guy would not be there, we will just have a j sitting in here, is not it? We will just have a j sitting in here. So, rho naught C naught is multiplied by U2 at z equals 0, this comes in denominator j. So, j times cot K naught L and it goes in the numerator. So, it becomes really tan later on, and here also we can simply sort of get rid of this guy, and there is obviously a j sitting in here, which I also forgot, my apologies again, but I will make amends. Minus sign is taken, that is correct. And what it would really mean is that coming back from this equation, minus T14 times P2 and this thing. So, cot goes in the numerator, it becomes tan, and j is multiplied in the numerator, denominator becomes minus j, okay. So, it becomes so, and obviously we need to get rid of this guy, is not quite correct. So, going back and checking things, minus T14 times this. So, cot becomes tan, as we can clearly see here, and T14 is multiplied by tan and P2 is taken out common. J is a denominator, j multiplied j. So, it becomes minus j, because minus j square is there. So, this is all good. Similarly for the second equation is also all right. So, we have this, my sincere apologies once again for the elementary mistake here, but this is what we get. So, things are looking good, they are looking sort of a bit more manageable. This is your 2 cross 3, this is 3 cross 1 matrix. So, all good. Now, we still have a bit more work to do, because this is, mind you, at z is equal to 0 and this is at z is equal to L. So, this variable is different from this one, in the sense that we are relating things at different sections. So, what do we do now? Basically, let us sort of write it down, and we would basically eliminate kind of P2 at z is equal to 0 from using either of the relations. So, let us use the third row thing. So, P2 at z is equal to 0 is T31 P1 tilde. I am just dropping the tilde sign for now, it is more convenient to do so here. T32 rho naught C naught U1, and T3 is taken common, minus T34 minus, I am sorry, this is also T34. Okay. So, minus T34 times j is in the denominator. So, actually it will become actually plus here, because j is multiplied, j square minus is cancelled. So, you get basically just j times tan K naught L B or something like that. So, here also we get pretty much the same thing, but what we get is also j, and this is j, where j is root over minus 1. Okay. And this is this thing, and this guy is sitting here. Basically, what it would mean is that T34 times j times tan K naught L B, that needs to be added to this guy to get us P2. So, this is all at z is equal to L. So, we have this sort of relation. Now, we can directly use this guy, put it here, I mean put the right hand side, I mean this thing, this entire thing here, and expand it out, and then we can completely eliminate, but be prepared for a rather nasty algebraic simplification. So, it does require some work. So, what we would do is write down the set of equations. So, P2 tilde at z is equal to 0, we can just directly copy this guy, T31 P1 plus T32 rho naught C naught U1 plus T33 plus j times tan K naught LB times T34, and this is multiplied by P2, I believe, yes, P2. So, this thing is divided by j cot K naught L A, okay, j times cot K naught L A. So, we just simply copied P2, what we got from this equation here, into this guy in the numerator, and just divide by j cot K naught L B. So, there is no problem with the minus sign here, and once we do that, we would just keep it aside for the time being and go back perhaps to this equation and expand this out completely. So, now all these variables, mind you, at z is equal to L, okay, and we have to patiently term by term multiply P 1, and everything is at z is equal to L, okay, and T43 plus j times T43, here it is the same thing, minus is there, so multiplied by j square minus cancelled, j times tan k naught LB, j times tan k naught LB times T44 is what you get, and P2 is again taken common. Okay. So, we get this. This should be abundantly clear. So, now and I think I would like to drop off this term, because it is understood that all the variables in this equation are at z is equal to L section. So, how about I sort of just multiply throughout with j cot k naught L and then go about simplifying things. So, with the idea that this thing P2 has to be expressed in terms of this thing. So, we could do that. So, basically what it would mean, let me do it on another piece of another slide. So, the idea is that this minus j times tan k naught L A into T31 minus T41 times P1 tilde is divided by x1, and similarly your the other term, that is your plus rho naught C naught U1 times, in the bracket it is negative, minus j tan k naught L A T32 minus T42 is divided by x1. Okay. So, we get this P2 thing, isn't it? We get this P2 thing. So, this entire thing, this entire expression, let me call this equation 2, is being, it has to be substituted in place of this thing. Okay. And then we again regroup terms in terms of P1 and rho naught C naught U1. So, it becomes, as you can see, it is already getting quite complicated. It is a good idea maybe to involve computer algebra, like for example Maple or something like that, to simplify matters, or at least just write a MATLAB code and let the code do all the simplifications for a given frequency. So, we could do that, and eventually what we would do, I mean, once we get P2 in terms of the big expression that we just discussed now, we regroup, and at the end of the day we will get a simplified, well, notionally it is simplified analysis. This is basically your P1 tilde rho naught C naught U1 in terms of the T1 matrix. So, T1 matrix is different from here, just the T matrix, it is this thing rho naught C naught U1 at z is equal to L, and this is z is equal to 0. Okay. So, at the end of the day what we have done, we have related things just at the point here, see the point at 0 to the point at L, taking into account all the complex things that happen in this annular region and the propagation, that the coupling due to this thing. Obviously, these two regions are uniform, so it would not matter much. So, it would not matter at all apart from change in phase. So, here to here we have related the transfer matrix, and using, once we get this T matrix, we can sort of do a lot of things. We can find out the transmission loss expression, use the same equation for transmission loss as that used for the classical state variables to get the stuff. Now, what really we have to do from now is that if you have more complicated things like cross flow expansion chamber and all that, in the next class I will probably, or maybe next to next class, these are lectures 1 and 2 of week 8. So, in the lecture 4 perhaps I would talk about other expansion elements. What I am going to do tomorrow, I mean in the lecture 3, is evaluate, do some MATLAB demonstration. Basically and actually before I do that, I will talk about present some popularly used perforate impedance expressions that is available in the literature, a very brief historical review, or probably just mentioning some important ones, starting from the work by Ingard and Munjal and Selamet and other guys, El Nadi, and there have been a lot of expressions. So, I will kind of present those expressions to you and the situations in which they have to be used only for the case of well grazing flow. That is what we are dealing here. Let us remind ourselves we are dealing with only grazing flow. So, I will present those expressions, and some of them actually involve mean flow, some of them do not really involve mean flow, but they have other effects. Well, once we do that, we would go to a MATLAB code and type in the appropriate perforate impedance expression zeta, what we have been figuring it out in the T matrix, and which is inherently presented, and incorporate all the boundary conditions and possibly analyze your fully perforated CTR with and without flow, and also present the analysis of CTR with extensions at the inlet and outlet, neck extensions or extended inlet and outlet, the perforated bridge without flow. But in this case, I had also introduced some empirical expressions for end corrections, which is popular, and then possibly do some mean flow parametric studies, I guess. But there is lots to be done even after doing that, because this is one of the basic elements. So, let us get sorted out with this first, and possibly in tomorrow's lecture, that is lecture 3, and also involving perhaps lecture 4, maybe lectures 3 and 4 would be combined, and then we will see what we will do in the lecture 5 for this week. So, till that time, stay tuned, and I will see you in the next class.